So now that we've looked at rotation, let's review translation in the plane. If we have a point xy, and that point is moved h units in the positive horizontal direction and k units in the positive vertical direction, then that movement can be represented by a vector v, and that vector has the components h, k, and of course the additive inverse of this vector is the vector negative v, which is the vector negative h, negative k. So a transformation takes the point xy and adds to that point the vector v, and so this produces the point x plus h, y plus k. And the passive transformation that corresponds to this active transformation is one that applies the additive inverse of the vector, and so that is takes the point xy to the point x minus h, y minus k. So let's look at an example. So let's translate the parabola x squared is equal to 4ay by the vector hk. Again, the active transformation takes the point xy to the point x plus h, y plus k, and the passive transformation takes the point xy to the point x minus h, y minus k. So to apply the translation to an equation, we use the passive transformation. So anywhere we see x, we replace it with x minus h, and anywhere we see y, we replace it with y minus k. And so the new equation for the translated parabola is the quantity x minus h squared is equal to 4 times a times the quantity y minus k. So let's look at what happens to the points. Let's look at what happens to the vertex, the focus, and the directrix. For the equation x squared equals 4ay, the vertex is the point 0, 0, and this is going to be translated by the active transformation to the point hk, 0 plus h, 0 plus k, and the focus is the point for this equation, x squared equals 4ay is the point 0a. So this will be translated to the point h, k plus a, and the directrix is the line y is equal to negative a. And so this is transformed to the equation y minus k is equal to negative a, or y is equal to k minus a. So for an illustration, let's choose a particular horizontal displacement of 2 units in the positive direction and a vertical displacement of 3 units in the negative direction. And let's plot our original parabola. X squared is equal to 4 times a times y. And let's make that a dotted line. And so now let's plot our translated parabola. And that is the parabola x minus h quantity squared is equal to 4 times a times the quantity y minus k. So let's look at our points. Our vertex for the translated parabola is at the point hk. The focus for the translated parabola is at the point h k plus a, and the directrix for the translated parabola is the line y is equal to k minus a. So next, let's translate the ellipse x squared over a squared plus y squared over b squared is equal to 1 by the vector v with components hk. Then again, the active transformation takes the point xy to the point x plus h y plus k, while the passive transformation takes the point xy to the point x minus h y minus k. And so to apply the transformation to the equation, we apply the passive transformation. And so the new equation is the quantity x minus h squared over a squared plus y minus k quantity squared over b squared is equal to 1. So let's look at what happens to the points. The center of the original equation is the origin. This point is translated by the direct or active transformation to the point hk, 0 plus h, 0 plus k. The foci, one of the foci of the original equation is the point negative a times the eccentricity e, 0. This point is translated to the point h minus a times e, k. And the second focus, AE0, is translated to the point h plus a times e, k. The vertices, one of the vertices occurs for the original equation occurs at the point negative a0. This point is translated to the point x minus a, k. And the second vertex, which occurs at for the original equation at a0, is translated to the point h plus a, k. The covertices, for the original equation, one of those is the point 0, negative b, and that point is translated to the point h, k minus b. And the second covertex of the original equation, which occurs at 0b, is translated to the point h, k plus b. And finally, for the directrices, the line x is equal to negative a over e for the original equation is translated to x minus h is equal to negative a over e, or x is equal to h minus a over e. And the second directrix for the original equation, which is x is equal to a over e, is translated to x minus h is equal to a over e, or x is equal to h plus a over e. Okay, so again, for illustration purposes, we will choose a horizontal displacement of 2 units in the positive direction and a vertical displacement of 3 units in the negative direction. And since I've used the variable k, I need a new variable for eccentricity. I'll choose v, and we'll set that at 0.6. And so now I can define my parameter b as a times the square root of 1 minus the eccentricity squared. So we'll plot our original ellipse, x squared over a squared plus y squared over b squared is equal to 1. Let's make that a little bigger, and let's make that a dotted line. Okay, so now we'll plot our new translated ellipse, and that is the ellipse x minus h quantity squared divided by a squared plus the quantity y minus k squared divided by b squared is equal to 1. So our new center is the point HK. One of the foci occurs at the point x minus a times the eccentricity k. Another focus occurs at the point h plus a times the eccentricity k. The vertices, one of the vertices occurs at the point h minus a k. Another vertex occurs at the point h plus a k. A covertex occurs at the point h k minus b, and a second covertex occurs at the point h k plus b. And finally, for the directrices, one of those occurs at the line x is equal to x, or rather h minus a divided by the eccentricity, and a second directrix occurs at the line x is equal to h plus a divided by the eccentricity. So as an exercise, translate the hyperbola x squared over a squared minus y squared over b squared is equal to 1 by the vector b with components h, k. Determine the equation. Center foci, vertices, and covertices of the translated hyperbola. Okay, so new theorem. The slope of the tangent line to a curve in the plane given by the parametric equations x is some function of t and y is some function of t at the point with parameter t is y prime of t over x prime of t, provided that x prime of t is not 0. So proof. Y prime of t is the derivative of y with respect to t. Using the chain rule, this is the derivative of y with respect to x times the derivative of x with respect to t. And so this is the derivative of y with respect to x times x prime of t. So if x prime of t is not 0, then we divide by x prime of t to obtain dy dx is y prime of t divided by x prime of t, where dy dx is the slope of the tangent line to the curve at the point xy, where since we have parametric equations, x is a function of t and y is a function of t, that is at the point with parameter t. So new definition, a normal to a curve in the plane is the line at a point P. A normal to a curve in the plane at a point P is the line perpendicular to the tangent at the point P. Okay, so we will end here for now. Next time we will explore the reflection laws and some applications of the conics. So I hope you have enjoyed the third lecture. Thanks for watching.